Yes. Well, people usually don't like porosity in ceramics because porosity decreases the mechanical strength of a component. But there are a lot of applications where actually porosity is extremely important. And people who work in generally porous materials would say that if you add porosity to a component, you actually add functionality to the material. And there are charts, plots that show how you can change a lot of every property of a material simply by adding porosity. So the amount of porosity that you can embed into a component will tailor the, for instance, mechanical property, thermal properties, electrical conductivity, permeability of the component for a specific application. So instead of being a drawback, porosity is actually an enhancer for a ceramic component in the sense that it widens up the range of applications that you can pursue with ceramics. Well, by engineering porosity, we mean tailoring the amount of pores and also the morphology of the pores. And by amount of pores, of course, you mean the total amount of porosity in the component, and that for a porous component, usually it goes from, let's say, 30 volume percent to up to 99 volume percent in, for instance, in aerogels, very lightweight components. They are described as air trapped inside a solid skeleton. So you can change the amount of porosity, and then you can change the size of the pores, and you can go from nanometer size pores, for instance, for hydrogen or gas separation membranes, or you can go to millimeter size pores for applications such as metal filtration, where you need a high permeability and at the same time you need to trap, for instance, unwanted components in the melt, like slag or other components. So changing the size and the amount of porosity is two ways of engineering the porosity in a component, and the third way is to change, for instance, the interconnectivity between the pores, meaning you can have close porosity, and that's useful for some applications, like of course, when you do not want a permeability in your component, or you can change the cell window size, the interconnection between the different cells, the different pores in the material. So by and you do this in engineering by usually selecting an appropriate processing procedure. You're mentioning a very important application for porous ceramics, or more specifically cellular ceramics, and there is a lot of interest in DPF filters for obvious environmental reasons. And there are several designs. Currently commercially available ones are based on honeycomb structures. And so it's not, it's a specific type of cellular ceramic, it's not a random channel, a random pore material. And with DPF filters, you have to have two levels of porosity. One is the microchannels that enable the low pressure drop of the component, and then you have the walls that instead of being solid, they are porous. And they enable to have cake filtration, meaning that the soot particles will deposit on the surface of the material, and the gases will pass through. And in order to have a low pressure drop, you need to work on the specifics of the interconnectivity of the porosity, the amount of porosity that you have, and then you have to add a lot of other stringent requirements, strict requirements such as thermal shock resistance and oxidation resistance, and then you need to add a catalyst for burning the soot at low temperature, for regenerating the filter. So that's a very good example of an important, industrially important and socially relevant application of porous ceramics. And you need to work hard in order to optimize all the different parameters. And the last one is cost, which is of course of great importance.